right, next we have Menachem. I'm afraid I'm going to butcher this, but I'll try. Sendigursi? No, I butchered it. All right, but go ahead.
Okay, thank you. In short, my name is Manny, actually, so that's long name can be reduced. And I'm going to talk about compression schemes for real-valued learners. This is a joint work with my advisor, Aryeh Kandrovich, and with Steve Henry. So let's start with the simple explanation of what are compression schemes, although you heard about it at least twice. So not to be confused with compression in the sense of coding theory, here on learning we're talking about a slightly different notion, defined here by two functions, kappa and rho, and the idea is the following. We start with a random sample, and our first function, kappa, is supposed to find some subsample, hopefully small, and maybe some side information, some explanation represented as a binary string. And what the second function should do, rho, it's supposed to take, knowing only this subsample and only this information, it's supposed to output some hypothesis. And what we want is that this hypothesis should be consistent on your original sample. Meaning, using this hypothesis, we can recover exactly the whole labeling of the sample. So we are not interested in recovering the points, but only their labeling. Think, for example, about SVM. SVM, well, its name is derived from supporting vectors, though in this case, those are 3 points. And those 3 points actually tells you the whole story of your labeling of your data. If you keep only those points, you won't be able to know what other points were in the sample, but you will be able to recover the labeling, all the labeling. So this idea, this notion was proposed by Littlestone and Wormuth, which also proved that if the compression size, if you have a class and a compression scheme for this class, which size, in size I mean the size of the output of kappa, the first function, the number of points you need to keep, and the length of the assigned information. If this size is independent in your sample size, and it's constant in a way, then you can use the compression scheme as a learning algorithm, as a path learning, meaning that your class is also learnable. Actually, you even on Friday you heard a talk proving that there are also sharp bounds for this lower bounds. What about the converse? So it was a long-standing conjecture that the converse should also apply, meaning that if you have a learnable class, here we're only talking about binary for now, so if you have a class with finite VC dimension, then it should also have some compression scheme whose size is constant, is independent in the sample size. Wormuth even gave it a more quantitative manner when he conjured that the size of the compression should be as small as the VC dimension, linear in the VC dimension. It took a lot of years, but a few years back, Moran and Yudayev proved that the conjecture is indeed true, meaning that if you have a binary class of VC dimension D, there is some compression scheme of size D times 2 to the power of D. I just note that the exponential factor here is due to the multiplication in the dual class, the VC dimension of the dual class, meaning that in a lot of cases, this bound actually can be reduced into linear, but on the general case, we're still on an exponential upper bound, meaning that the conjecture by Wormuth is still open, at least from my knowledge. But we will go in another direction and ask, what about regression? More specifically, if you have a class of real-valued functions which has a finite fat shattering dimension, does this imply that the classes also have some compression scheme whose size is constant, is independent in the sample size? So just to make things clear, because we're talking about regression, to aim for exact reconstruction or delabeling is not so reasonable. So we will settle for a slightly less than that, and we will, instead of consistency, we will aim for approximate uniform consistency, meaning that we wish to bound our recovering, the maximal error of our recovering by some parameter, fixed parameter, small one, we'll call eta. To do so, we had to take the ideas by Moran and Yudayev and do a little bit of refined analysis. And to do that, we called for a close and very famous friend, the boosting. The connection between boosting and compression scheme is actually as old as the day of the boosting from the early 90s. But when we're talking about boosting, and again, not binary classification, but regression, first you have to ask, what does it mean to do a boosting on a real valued function? And the more basic question you have to ask is, what are weak learners or weak hypotheses when you're treating real valued functions? Well, you might say, let's go with the straightforward analog, which just means look about the expected loss and just use, instead of 0-1 loss, you can use whatever continuous loss, L2, L1, whatever you like. And just as we're talking about weak hypothesis, you need to bound this expected loss with less than half minus some parameter gamma. It turns out that when you talk about algorithms like boosting by majority and the like, this definition just fails, because this definition bounds the expected loss, meaning a quantity which is, in a sense, global. It's a quantity of your whole space. So what can happen is that your loss can be spread evenly all across your data, meaning that when you do the boosting by majority tricks of manipulating some synthesized distribution on your data, it's just meaningless. So what we have to look for is some more uniform notion of loss, of weak hypothesis. And it turns out there is one. It's the following. Notice here that what we're bounding, if you take all the points, each point on your space, and you let's call the points which differ too much, more than this parameter eta, they differ from the ground truth too much. Let's call them bad points, and what we want is that the number of the bad points to be not too much, or to be less than half in this case, because we are again talking about weak definition. It turns out that this definition is actually a special case of the good model definition proposed by Hans Simon. It's a less known one, but for our needs, it's the better one. We're starting, so back to our mission. We started from a learnable class, a real valued function learnable class, meaning we have a finite fact-shattering dimension. So how can we produce those good model or weakly good model when all we have is a learnable class? So our first result was to prove some sample complexity upper bound, meaning that if you have an year M on your class, or even actually an approximate year M on your class, this amount of points will be enough to produce a good model. Note that the main factor here is just the linear factor in your fact-shattering dimension. And it is, again, a special case. If you plug in the right parameters, you get a weakly good model, which was what we needed. So now, when we can finally produce those weakly hypotheses, we can now boost, and for that, we use a boosting algorithm called MetBoost by Kegel. This is a really vague outline of the algorithm. What you do, again, it's boosting, so what you do is iteratively pick some random subsample, you plug it into your weak learner, you get an hypothesis, you assign some weight to your hypothesis, and adjust the distribution accordingly. You do that t times, and you get an ensemble. the point is that this ensemble has the median actually of this ensemble, and hence the name. The median has an error which decreased exponentially. More specifically, we proved that that if you take the number of iterations to be log m, when m is your sample size, you get a maximal error of eta, the same parameter we fixed before. So, what do we got so far? We have an ERM, approximate ERM, for some generic one. We produced, using a number of samples of the size of the fat shattering dimension, we produced weak hypothesis, weak learner, and we did that log n times to get an ensemble. An ensemble which is, again, approximate uniform consistent. If you store only the points used to define those hypotheses in the ensemble, you get that we can store only number of points which is log n times the fat shattering dimension of your class, instead of the whole m points of your sample. So that's a compression, but we aimed for a compression which size is independent in the sample size, and here we only got a log n, so we have still a gap to close. And to do that, our idea, our strategy, was to just look at the ensemble of the ensemble again of log m size, and to sparsify it using just picking at random some small sub-ensemble. And the main issue here was to figure out which size will be enough. From one hand, enough meaning we would still hope to get an ensemble which is approximate uniform consistent, and from the other hand, you need this sub-ensemble to be small enough to get rid of this log factor. So we proved using some margin-based analysis and ideas that the right size for this mission is actually the fat shattering dimension of the dual class, which is worst case is exponential in the fat shattering dimension of the primal class. And if you pick your ensemble of your sub-ensemble to be from this size, you get that from one hand we got rid of the dependency in the sample size, but from the other hand we still have an ensemble which is approximate uniform consistent. So to sum up, we use an ERM on the samples of the size of the fat shattering dimension. We did that log n times. We'll use MedBoost in order to get an ensemble which is approximate uniform consistent. And then as a final step, we sparsified it randomly into a sub-ensemble of the size of the fat shattering dimension of the dual class, resolving in a compression scheme of size of the multiplication of the both, which is independent in our sample size. And that's it.